All right, let's talk through chapter 17 here, talking about the sun. Let's talk about what it's made out of, the solar cycle, what that is, what's going on above the surface, and space weather. Okay, so sun's a big ball of fire, huge. There's the Earth for scale. Very, very large thing. There's a prominence shooting off the side. Let's see. So, the mean distance we are from the sun is about 1 AU by definition, 150 million kilometers. There's some masses here. It's 300,000 Earth masses about. Pretty big ball of fire over there. Let's see here. Anything else important? No. There's the luminosity in watts, joules per second. It's a type G2 star. There's your spectral type. The effective temperature is 5800 Kelvin, so that would be the surface temperature of the sun. When you look at it, what you see is a 5800 Kelvin black body irradiator. It takes about 24 days for the sun to rotate once, and you can watch the sunspots move across the front of the sun and get an estimate of the time it takes. Okay, so sun's atmosphere is made of elements. Mostly hydrogen. 92% of the atoms in the sun, 92% are hydrogen. And by mass, it's about 75% hydrogen, 25% helium. So we've already converted about 25% of the hydrogen in the sun into helium. So there's about 75% remaining for fusion in the core before it runs out of hydrogen to burn. And then you've got a trace number of heavier elements here, very, very small amount of them, less than a tenth, or in some cases 1/100%. So very, very small amounts of heavy elements, which we'll talk about later why that's important. Okay, the famous person here, Cecilia, she discovered that hydrogen and helium are what all stars are made out of. She was the first woman to get a PhD in astronomy in the United States. This was a big deal. Okay. Before this, we assumed the sun and stars would be much like that of Earth, and it took a while before we realized that it was indeed hydrogen and helium, and that there's something else going on rather than friction causing the heat. Okay. The sun is a plasma. It's a ball of gas. And that's where the atoms, normally you have a proton, normally you have a proton or several protons and electrons orbiting it, and that's what makes an atom an atom. Well, if you put enough energy into the system, the electron can just fly around, and then the proton is just free to do its own thing. So you could have one proton there, you could have two protons, and now you have helium, or you could have three protons, so these are three different atoms, and then the electrons aren't bound to them, they're just zipping around because the temperatures are so high. That's what makes it a plasma. Okay, so the sun, make sure you know these layers. You've got the corona, that's the atmosphere, that's the outer area of it. The photosphere is what you see when you look at it with your eyes. Don't look at it very long. A sunspot on the surface is a local area that's a little bit cooler, so it looks a little bit darker. The chromosphere is this sort of layer just above the surface. A coronal hole here is just an area where, excuse me, and you've got the core, and the core of the sun is right in the middle there. The radiative zone is where you can see the arrows are showing that the energy is just flowing out from the core, and then as it gets to the convection zone, it loses energy and kind of toils around. So that's what these convective zones are. Okay, so the important thing here is that all the layers are different and each plays an important part. Okay, so just learn those different areas. You've got your core, then you've got the radiative zone, then you've got the convective zone. Okay, the solar photosphere, approximate size of the Earth here, compared to the sun. The photosphere is what you see with the sun, so it's the apparent surface of the sun where the density of the sun suddenly drops and goes into outer space basically, and we can't see further into the sun from that point, so we call that the photosphere. Okay, and when you look closely at the surface of the sun, it has this feature called granulation, and that's from convection. So granulation happens when the sun basically boils, and the surface has this turbulence, and that creates these kind of pockets where the different turbulent layers form together, and then you get this really wonderful looking granulation. And so that's all these little cells, looks like honeycombs almost in a beehive or something like that. And there's a sunspot here, zoomed in there to show you what's going on. Okay, so that's granulation. Make sure you know that one. So the chromosphere is a layer just above the atmosphere, just above the photosphere, so it's part of the atmosphere. And the chromosphere is just right above it, and you could only really see it when the moon kind of covers the sun, and allows you to see the edge of it. It's this kind of streak. Now we can look at it with special telescopes and different emission wavelengths. Okay, so the transition region basically is where the temperature rises pretty quickly as you get away from the sun. So the surface of the sun is about 5,000 degrees, so that's what this is showing here. As you go away from the surface of the sun, you enter the chromosphere, still about the same temperature, and then zoom, when you get to the corona, it goes up to 1,000,000 degrees. So you're going from thousands of degrees at the surface to millions of degrees up in the area. And remember what temperature is. Temperature is just the motion of atoms. So if you have a low density material, you could have the atoms moving around at a very high speed, and that's how you can get very high temperatures at that area just above the sun. So you got this gas here, which is pretty cool. And there's the surface of the sun here, and then the sphere, chromosphere, and then the atmosphere there. Okay, so then the corona is the outermost area, and so this is from SOHO picture, and that white ring there, that's the sun. This is a screen that's blocking the sun out, so you can't see it. So all you can see is this flowing energy away from the sun. Okay, and then that energy that you're seeing there is the chromosphere. The corona. And so by looking at the corona, you can learn about space weather and how the sun, solar radiation sort of affects the rest of the planets. So this corona, as it goes out, it starts to be a part of what's called the solar wind, and it's this stream of particles, protons and electrons, that are just shooting out all the time. They flow out from the sun at 1,000,000 miles an hour, okay, and then come flying at the Earth and all the planets. So luckily we have a magnetic field, and the interaction with the sun and the Earth creates an ionosphere, and then the solar wind, when it interacts with our magnetized force field that's around the Earth, it kind of prevents these things from reaching us. Okay, there's coronal holes, which are just large dark regions of the corona that are relatively cool. So that's where you can see, there's a nice coronal hole there at the South Pole. Okay, so this is looking at I believe this is a ultraviolet image showing you light in the ultraviolet wavelengths. So at the very, very high energies of just beyond the visible spectrum. Okay, the aurora that you see, the nice beautiful colors up here, that's from the solar particles from the solar wind hitting the atmosphere. When it does that, it ionizes the atmosphere, causes it to glow, and so the sun is causing the aurora when it interacts with the magnetic field. Okay, so the solar cycle is a period where let's see if we got a picture here. So here you go. Here's the sun over 10 years, basically. And so year 1, year 2, year 3, year 4, year 5, year 6, year 7, year 8, year 9, year 10. And what you can see is that in year 1, you have a ton of sunspots all over the sun. By year 5, year 6, between there, you've got almost no sunspots on the sun. And then back by year 10, you've got sunspots breaking out again. And that happens every 11 years. So every 11 years, the sun goes through this cycle. That's called the solar cycle. And what happens is the magnetic field actually stops and allows when the magnetic field stops flowing out from the sun, it reduces its ability to contain all the plasmas to prevent the sunspot from going crazy. So when you see the sun with a bunch of sunspots on it, it doesn't have a very strong magnetic field at that point. When you see the sun with no sunspots, that means it has a very strong magnetic field that's keeping the surface of the sun contained. Okay. And above the whatever. So you got these plages and prominences. Yeah, look at these things. So here's the size of the Earth. You've got a large prominences here. And these are big eruptions. They usually follow magnetic field lines. They shoot these particles out into space, and you get these coronal mass ejections and other things. I mean, look at these beautiful flares shooting off the sun. So those are called prominences. And what can happen is you can get a CME, which is a coronal mass ejection. And a coronal mass ejection, basically you get a ton of particles just shooting out. Yeah, look at this. It says the largest flares last for several hours and emit enough energy to power the entire United States at its current rate for 100,000 years from just one solar flare. So that's a ton of energy shooting out of the sun. Okay, you can see here the sun, again, is in the white circle here, and there's a disk blocking it out. And you can see this huge ejection coming from the sun. And then same thing, as you zoom out even more, you can see this huge ejection just shooting out into space. So those are called coronal mass ejections. They can affect the Earth a bunch of different ways, and which we'll talk about in the space weather section. Okay, so there you go. There's your solar cycle again, 1996 to 2006. You can see the sunspots just breaking out all over the surface and then disappearing back by the end of it. Okay, and then you can see the same sun, 1, 2, 3, 4 pictures, same picture, different wavelengths. 171 angstroms, 304 angstrom, 335 angstrom, showing you the ultraviolet pictures of the sun. Okay, so just really amazing. Check that out. Pretty cool. Okay, so anyway, space weather. Sources of space weather. So this is when the sun has a CME, coronal mass ejection. The particles can fly through and damage circuits and satellites and communication systems, and can also mess with power systems. So in 1989, there was a large one. It took power out in Canada just from a solar storm. So that's crazy, right? You got problems with airplanes, astronauts, satellites, all sorts of stuff that we have to keep an eye on. So that's why we track the space weather for warning satellites and other systems to make sure they don't get affected by the space weather. Okay, so there's no connection to the solar cycles and Earth's climate. There is a slight change in the temperature. Sorry, I just zoned out for a second. Okay, so anyway, so the issue with this is that the change in output from the sun, even during the solar cycles, when it goes from a peak to a minimum, there is a change in the output energy of the sun, but it's quite small. So we don't think that so the energy output from the sun during a solar cycle varies by about 0.1%. There's no evidence that that small of a variation can change the temperature of the globe, but there's other ways that the solar cycle does affect us. For example, changing the amount of UV light that's coming out from the sun. So that changes the atmosphere and some other things about the sun. But anyway, it's pretty tricky. Okay, and that's the end of that chapter. Okay, so just make sure you understand those areas of the sun, understand that the sun has a solar cycle, understand that there's coronal mass ejections and space weather that comes as a result of those ejections. Okay, see you later.